All right, welcome. This is Ralston Valley High School AP Chemistry's lecture series, Chapter 17, Lecture number 2, in which we're going to investigate electrochemistry, specifically cell potential, work, and free energy. Let's get started. All right, to begin our conversation here today, let's start with the recognition that chemical potential energy can be used to do useful work. This is something which we see all around us on a daily basis anytime we use a device which has a battery. And those devices that have batteries can be used to change chemical potential energy into mechanical energy in a wide variety of devices, from electric drills all the way up to bigger things like electric cars. And as it turns out, the work which is done by this movement of electrons through a circuit is dependent upon a thermodynamic driving force which moves those electrons. We call that thermodynamic driving force the electromotive force, or EMF for short. That electromotive force is essentially related to a concept which you first explored back in your days in our physics classes, in which you looked at an idea of a potential difference, or a voltage. By definition, a voltage, you may recall from physics, is the amount of work per unit charge. That is, the unit 1 volt is defined as a joule of energy per coulomb of charge. Now, if you think back to our previous conversation we had about galvanic cells, recall that a galvanic cell has a positive cell potential, that is, a positive voltage. And that galvanic cell can be used to do work on its surroundings, that is, transfer energy from the system to the surroundings. And as such, we would like to derive an equation that describes the relationship between the cell potential, which in our equations you're going to see notated with this little cursive E, how that cell potential is related to the work which is done by that system. And as it turns out, we define the cell potential as being minus the work done divided by the charge. And recognize again that the value here for cell potential is going to be the opposite of the work done, that is minus work, because if the system itself does work on the surroundings, the potential energy of the system must therefore decrease. So we got a negative there to notate that we're essentially seeing the system lose energy in a system where the cell potential is positive. Now, again, looking at that cell potential, if we see the units here, work is essentially in joules and charge would be in coulombs. We see therefore that cell potential would be therefore joules per coulomb, which is in volts. Now I could rearrange that equation to solve for the work done by multiplying both sides of my equation by the charge Q. And as such, I would get a new expression, which is the work done would be equal to minus the charge Q times the cell potential of our system. So long story short, if you have either, number one, a larger amount of charge which is moved, you would have the ability to do more work, which explains again why the longer you have your device plugged in, the more work you can do. Or number two, if the cell potential is greater, you would be able to do more work as well, because the amount of energy carried per unit of charge would also be larger in that instance. So essentially work is both directly related to the amount of charge moved Q, as well as the cell potential E in our system. So now that we understand the relationship between cell potential and work, let's move on to our next slide. All right, continuing our conversation about the relationship between cell potential and work, I'd like to introduce to you here a new unit of measurement which we refer to as a Faraday. A Faraday, by definition, is a unit of measure equivalent to the charge on 1 mole of electrons. And specifically, we define a Faraday as the value of 96,485 coulombs of charge per mole of electrons. Now, with that defined value of a Faraday, we can see that we can develop now a relationship that exists between charge and a number of moles. That is to say, the charge Q, which flows in a system, would be equal to N, the number of moles of electrons transferred, times a Faraday. And we understand here, looking at the units there, that makes logical sense, as N is moles of electrons, and Faradays are coulombs per mole of electrons. So as such, if you multiply those two values together, you would have coulombs per mole times moles, which would therefore just yield units of coulombs of charge moved. So here is a key idea that we're going to use to tie together two fundamental concepts of our last couple of units. Recall that the maximum amount of work that we can do by a chemical system is equal to the change in free energy of that system. That is to say, the max work is equal to delta G. Also, from our conversation we've just developed right here on our previous slide, remember that the work which is done by a chemical system would be equal to minus the charge Q times the cell potential E. And because both of these two expressions fundamentally solve for the work done by a chemical system, I could essentially set them equal to each other. That is to say, the change in free energy of the system, delta G, must be equal to minus the charge Q times the cell potential E of our system. And looking back to the conversation we just had above relating charge to Faraday's, recall that the charge Q for a system was equal to the moles of electrons N times a value of a Faraday F. I'm going to go ahead and substitute that value NF into Q in our expression here, yielding now an expression which is the change of free energy is equal to minus the number of moles of electrons times a Faraday times the cell potential E. And if we run a reaction under standard conditions, that is for a thermodynamic system at a temperature of 25 degrees Celsius, and for aqueous solutions at concentrations of 1 molar, that would therefore yield here a new expression which is the standard change in free energy of a electrochemical system would be equal to minus the moles N times a constant, the Faraday, times the cell potential E under those standard conditions. And importantly, note here, folks, that we now have developed a new tool that allows us to solve for a change in free energy. And remember from our previous conversations in chapter 16, the free energy is really the concept that fundamentally links together so many of our different units. We've seen previously that free energy can be related not only to calculations in thermodynamics, but also calculations in equilibrium chemistry. Now we see it also has applications in electrochemistry as well. And importantly to note, recalling from our conversations in chapter 16, recall for a spontaneous process to occur, the value of delta G must be a negative value. And therefore, for a spontaneous process, again, we have a quantitative proof now that the value of the cell potential, that is E naught, must be positive. So, to summarize, we now have a new tool available to us, a new equation that allows us to calculate a change in free energy of a system, that is delta G naught is equal to minus NF times E naught. And additionally, an observation of a positive cell potential for a system can therefore also now be used to prove that a process is thermodynamically favorable, that is, we have a spontaneous reaction occurring. All right, let's now apply these ideas in our next slide. All right, so now that we've derived some equations over the last couple of slides, let's see if we can apply these to determine here a calculation of the free energy for a redox reaction. In example number 1, we're going to ask you here to calculate a change in free energy under standard conditions for the reaction described below, and then to determine if this reaction would be expected to be spontaneous. And the reaction we're going to have you look at here is a reaction in which we're taking copper 2 ions, Cu2 positive, in aqueous solution, and reacting them to iron in solid state to form solid state copper as a product, and also iron 2 ions, that is ferrous ions, in aqueous solution. And we're providing you here with a table of reduction potentials. Recall we met this table of reduction potentials previously in lecture 1 out of chapter 17. So let's go ahead and have a look here at the reaction as written and determine here, first of all, which species are being oxidized and which species are being reduced, and then identify the corresponding half reactions. Starting off with the copper. The copper initially is in a +2 oxidation state on the reactant side. Over on the product side, it is elemental, so in a 0 oxidation state, implying the copper ion is going from a +2 down to a 0 oxidation state, therefore it must be reduced in this system. So I'm going to go ahead then and write the reduction half reaction for that process. The copper 2 ion, Cu2 positive, picks up 2 electrons, and in doing so forms Cu elemental. And I'm going to now find that half reaction on our given table of reduction potentials. Searching along here, I find a standard cell potential for this half reaction of 0.34 volts. Now for the second process, which is occurring right here, I've got a reaction in which the elemental iron reactant here, that is Fe elemental in solid state, is reacting to form ferrous ions, that is Fe2 positive, on our product side. And to do so, it must be giving up 2 electrons as it is oxidized. Now remember, the table we have provided you with here is not a table of oxidation half reactions, that is, it is a table of reductions. So what I want to do then is look for the opposite process that we just described there. That is, we want to find here the reduction of ferrous ions, Fe2 positive, to form elemental iron. And I can find that there written as Fe2 positive plus 2 electrons forms Fe elemental, and it's listed here with a standard cell potential of this half reaction of negative 0.44 volts. So I've written out the reduction reactions for each of the 2 processes which are occurring here. But remember here that the iron species here is undergoing an oxidation, not a reduction. So I'm going to take that reduction half reaction we wrote right there and flip it around, turning it into an oxidation half step. That is, Fe elemental is forming Fe2 positive and 2 electrons. And because I have now reversed that reaction, that implies, therefore, I must also flip the sign on our cell potential for this particular half reaction. Therefore, now I have a standard cell potential of the half step of positive 0.44 volts for our oxidation of elemental iron. And at this point, I can now combine together the 2 half reactions to get the overall process. Canceling out the 2 electrons on both sides yields now for me Cu2 positive plus Fe elemental forms Cu elemental plus Fe2 positive. And I'm also going to now sum together the cell potentials of our half steps. Adding the positive 0.34 volts from the reduction plus the positive 0.44 volts from the oxidation yields now a standard cell potential for this overall redox reaction of 0.78 volts. And at this point, we now have enough information to calculate a value of the standard change in free energy. From the equation we derived on our previous slide, the standard change in free energy is defined as minus the moles of electrons transferred N times the constant of Faraday times the standard cell potential of a reaction, which for our particular process here would be minus 2 moles of electrons, as we are transferring 2 moles of electrons during the course of this overall reaction, times the constant of Faraday, 96,485 coulombs per mole of electrons, times the cell potential here, which was 0.78 volts, which I'm specifically going to now write out rather than in volts, but instead in joules per coulomb, that is a derived value of a volt. And as I do so, notice here that coulombs of charge are going to cancel out, both in my numerator and denominator, as well as moles of electrons, yielding then an answer in units of joules. And as I plug this into my calculator, I get a value of negative 150,516.6 joules per mole of reaction, which I could then convert here into essentially, with sig figs, negative 150 kilojoules per mole of reaction. And I now have sufficient data to support that this, in fact, would be expected to be a spontaneous process for 2 reasons. Number 1, you'll see here the value of my change in free energy is negative, and a negative change in free energy, recall, implies a positive change in entropy of the universe, and therefore a spontaneous process. And also number 2, the cell potential of our overall cell was positive, again implying a spontaneous process. All right, so we see some links between free energy and cell potential that allow me to now determine spontaneity. Let's move on to our next slide. All right, for our next topic of conversation here, we're going to investigate how the cell potential of a cell might be dependent upon the relative concentrations of reactants and products within our system. And logically speaking, it should make sense to us that if we change the concentration of a component of an electrochemical cell, we're likely going to see a change in the measured cell potential as well, essentially due to reasons related to Le Chatelier's principle. We know that by changing the concentration of a reactant or a product, I can increase the favorability of a forward or reverse direction reaction, which in turn should therefore impact the driving force on that electrons, that is the electromotive force, EMF. and therefore we see a change in cell potential. As a kind of general overview, if you see an increase in the concentration of a reactant, that would therefore increase the favorability of the forward direction reaction according to Le Chatelier's principle, which in turn should therefore see an increase in the cell potential. Conversely, if you see an increase in the concentration of a product, that would therefore increase the favorability of the reverse reaction, and therefore we'd expect to see a less favorable forward process resulting in a weaker driving force, a decrease in the cell potential. So let's go ahead now and apply this line of logical thinking to an example problem. In example number 2, we're going to ask you to predict if the cell potential of the described cell would be greater or less than the cell potential under standard conditions given the set of concentrations we're providing you for our examples. The cell we're going to have a look at here is the cell in which we're taking elemental aluminum in solid state and reacting that to manganese 2 ions in order to form aluminum ions Al3 positive and elemental manganese Mn solid. And we're giving you here a standard cell potential of 0.48 volts, implying here we've got a positive cell potential, thus a spontaneous forward process. Now, the first set of conditions we're going to investigate here is what if the concentration of aluminum, Al3 positive, is 2 molar and the concentration of manganese, Mn2 positive, is 1 molar. Recall, by definition, the standard conditions for aqueous species for all of our thermochemical data is always concentrations of 1 molar, which implies for this system, we are increasing the concentration of the product, Al3 positive, to a higher concentration than it would be under those standard conditions. By Le Chatelier's principle, if I see an increase in concentration of a product, that should therefore increase the rate of the reverse reaction, driving that reaction to the left, which would therefore decrease the driving force on those electrons in the forward direction, and as such, I would expect this system to see a cell potential which would be less than the standard cell potential that was given to us in the example. Now conversely, for the second set of conditions we've given you here, we're going to start off with, again, aluminum now under standard conditions of 1 molar concentration, but the manganese 2 ion now is listed with a concentration of 3 molar. In effect, we are increasing the concentration now of a reactant, which should therefore increase the favorability of the forward direction reaction by Le Chatelier's principle, and as such, I would now expect to see a cell potential of this cell in operation, which would be greater than the standard cell potential we would expect to see under standard conditions. So therefore, again, we would see a cell potential larger than 0.48 volts for this particular cell overall. So, long story short here, just a quick qualitative understanding of Le Chatelier's principle is sufficient to determine whether a cell potential of a given cell operating under non-standard conditions might be greater than or less than the cell potential under standard conditions. Let's move on to our next slide. All right, so having seen on our previous slide that the cell potential of a cell operating under non-standard conditions will be dependent upon the relative concentrations of the reactants and products in the system, we can now develop a kind of unique cell here, which we're going to call a concentration cell. A concentration cell is, by definition, a galvanic cell in which each of the compartments within the cell contain the same components, with the only difference between the two cell compartments being a difference in concentration of reactant species present. Now, as it turns out, a concentration cell, not surprisingly, like all things, will tend to approach its equilibrium position, in which the concentrations within each cell would be equal. And it should make logical sense once we reach this equilibrium position that there should be, therefore, no further net flow of electrons, as once those two half cells reach equal concentrations, the two half cells at this point would have equal cell potentials, and therefore the difference in cell potential between the two cells would therefore be 0, resulting therefore in no net driving force pushing electrons through our circuit. So, with that idea in mind, let's go ahead and take a look at now another example problem here, in which we're going to ask you to determine the direction of electron flow within the cell which is diagrammed to the right. This is a concentration cell based around a redox reaction involving silver elemental electrodes and aqueous solutions of silver nitrate in each of our reaction compartments. The difference here being on the left-hand compartment, we have a concentration of that silver nitrate solution of 0.01 molar, and on the right-hand side, we have a concentration of silver nitrate of 1.0 molar. So let's go ahead and start here with a quick description of the actual reaction that would be taking place in these two cells. Starting off here, we recognize that we have to have in one location an oxidation occurring and in one location a reduction occurring. Now, the oxidation which is likely to occur is the oxidation of the silver metal electrode. I can go ahead and write a half reaction here in which elemental silver, Ag, loses an electron and in doing so forms Ag positive ions in solution. Now, conversely, the reduction which is going to occur is going to be the exact reverse of that process. That is to say, a silver ion in solution, Ag positive, could pick up an electron and in doing so could form elemental silver, Ag elemental. Now, logically speaking here, the rate at which reduction occurs should be proportional to the concentration of the silver ions which are in solution. That is to say, if you have a higher concentration of silver ions in solution, they're more likely to be able to pick up those electrons, and therefore we would expect to see a faster rate of reduction in the cell where there's a higher concentration of silver ions. And in that case, that looks like the right-hand side over here. So I'm going to go ahead and label here the half cell on the right as being the cell in which we expect to see reduction occurring. That is, this is the cathode in our concentration cell. Now, conversely, that must mean that the oxidation would be happening within the other half cell, that is the left-hand side here. So I'm going to go ahead and label this one now as my anode. And as I've now labeled my cathode and my anode, I can now understand the process that should be occurring within our system. As the anode is where oxidation occurs, I would expect to see the silver electrode on the left side here giving up electrons and in doing so forming silver ions in solution. And those electrons then would travel along that wire across that voltmeter here towards the electrode on the right. So I'm going to go ahead and label now the direction of electron flow as going from the anode on the left towards the cathode on the right. And note as we do so, we are now increasing the concentration of silver ions within the left-hand half cell and decreasing the concentration of silver ions in the right-hand half cell. And as those concentrations are changing within each of the cells, that is, the left-hand cell will see the initial concentration of 0.01 molar silver ion increasing over time, and the right-hand cell will see that initial concentration of silver ion of 1.0 molar decreasing over time. At some point, those two cells will reach a point where the silver ion concentrations are equal in both cells. And at that point, we will have a system where the favorability of oxidation or reduction in either cell is exactly equal, and therefore that system will reach a point of equilibrium. And that's really kind of a key idea here, because once we reach that point of equilibrium, there's no longer a thermodynamic driving force or an electrochemical driving force causing this process to occur, implying, therefore, we will no longer see a movement of electrons once we establish that equilibrium in our system. And really what's happened there is that our cell is essentially now a dead battery cell. Dead battery cells are not cells in which all of the reactant has been consumed, but instead are cells where the system has reached its point of chemical equilibrium. And as it turns out, this idea we've just developed right here is a very big deal, which is going to allow us to develop a very, very powerful equation on our next slide. Let's move on and see. All right, over our last couple of slides, we've come to an understanding that the concentration of the cell components within an electrochemical cell affect the operating cell potential of that cell overall. And what we'd like to do here on our new slide is to develop an equation that describes quantitatively the dependence of that cell potential on the concentration of those cell components. In order to do so, we're going to start with, again, a couple of our definitions of changes in free energy. Earlier in this set of slides, we developed the idea that the change in free energy of an electrochemical system can be calculated by taking minus n, the moles of electrons, times a Faraday F times the cell potential E. And also, from our previous work during our chapter 16, we saw that the change in free energy of a system operating under non-standard conditions can be calculated by taking the change in free energy under standard conditions and then modifying it by adding the quantity RT times the natural log of the reaction quotient Q. If you'd like to go back and see where we have derived that equation, you can go ahead and have a look back to our lectures from chapter 16. Now, as both of those equations fundamentally represent a calculation of a change in free energy, we can therefore set those equal to one another. So we get now an expression which is minus NF times the cell potential E would be equal to the standard change in free energy, which again I'm going to substitute now minus NF times the standard cell potential, plus that factor RT times the natural log of Q. And at this point here now, I'm going to go ahead and just do a quick rearrangement by dividing both sides of that equation by the value minus NF. And as I do so, I get a new expression, which is now the operating cell potential, E cell, of a cell operating under non-standard conditions could be calculated by taking the operating cell potential of the cell under standard conditions, that is E naught, minus the factor RT over NF times the natural log of Q. And what you see here is we now have a new expression that will allow me to calculate how a cell potential changes depending upon the conditions of the system, both in terms of temperature as well as in terms of the relative quantities of the reactants and products present as expressed by that reaction quotient Q. Now, you might see a different version of this equation, which we call the Nernst equation, probably the most powerful equation we'll use over the course of our discussions in electrochemistry. Oftentimes, you'll see this expressed as the value E cell is equal to E naught under standard conditions minus 0.0591 over N times the log of Q. And really all we've done there is apply a set of standard conditions here at a temperature of 25 degrees Celsius, and then we've done a quick conversion to change the natural log into a regular old log there. So either one of these two versions of the Nernst equation can be used to calculate the cell potential of a cell in operation when it's under non-standard conditions. And now that we've derived this Nernst equation, let's think for a moment about how it might operate in the real world. Imagine for a moment here that we have a system with a large value of Q. As that value of Q increases, what that really tells me is that as Q, as always, is defined as the ratio of the concentration of the products over the reactants, a large value of Q would imply a higher relative concentration of products present in that system. And with a larger value of Q, mathematically speaking, the factor RT over NF times the natural log of Q, that whole factor as a whole, would also be increasing. And as we are subtracting that factor RT over NF times natural log of Q from the initial cell potential of our standard cell, that would imply that for higher values of Q, the operating cell potential E cell would therefore be expected to be smaller than it otherwise would be under standard conditions, which again makes logical sense. If we have a large value of Q, we've got a lot more product, which should increase the favorability of the reverse reaction, decreasing the cell potential of our operating cell. Now, conversely, if we have a system with a very, very small operating value of Q, as Q again is the ratio of products over reactants, that would imply in that system there would be a relatively higher concentration of reactants present. And with a relatively higher concentration of reactants, from a perspective of Le Chatelier's principle, we expect that would therefore increase the favorability of the forward reaction and therefore increase the operating cell potential of our cell. And the math backs that up again. If the value of Q is small, then the factor RT over NF times the natural log of Q would itself also be small, or potentially even negative if Q is a value less than 1. And therefore, we would expect to see a larger operating cell potential as that factor again is being subtracted from the initial standard cell potential of our cell overall in the Nernst equation. All right, let's see if we can go ahead and apply this to an example problem on our next slide. All right, so having now derived the Nernst equation on our previous slide, we'll go ahead now and have a look at applying this to describe more completely a cell in which some of the components are operating under non-standard concentrations. We are providing you here with cell notation describing a electrochemical cell where the first half cell is composed of a zinc electrode, and then we've got a solution of aqueous zinc ions at a concentration of 1.0 molar. That is against standard concentration. And in our other half cell, we've got a platinum electrode here. And then within the solution, we've got a variety of different species, including VO2, 1 positive, a polyatomic ion there in concentration of 2.0 molar, hydrogen concentration of 0.50 molar, and the VO2 positive ion, whose concentration here is given as 0.010 molar. And based upon this cell notation, we're going to ask you to write and completely balance a chemical equation describing the cell. We will also ask you to find the operating cell potential, that is E cell, for the cell as it operates under non-standard conditions. And then also we're going to ask you to draw and label a diagram depicting the cell showing the location of the cathode, the anode, and the direction of electron flow. So lots of things to accomplish here. Let's go ahead and get started. First of all, you're going to need access to a table of standard reduction potentials. You either may refer to the table which is given to you in your book, or alternatively, you can refer to the handout sheet you should have received that gives the list of standard reduction potentials that is provided to you as part of the AP test. So looking on that table of reduction potentials, I'm going to go ahead and locate the reduction reactions described within each of these half cells. Starting off here with the reduction of zinc ions, Zn2 positive, as they pick up 2 electrons to form elemental zinc. And as I search here, I find that reaction listed here with a standard operating cell potential of negative 0.76 volts for that half reaction. Now for the other one, that is this half reaction involving these vanadium oxide species, I find here on my table of reduction potentials here a reaction described as VO2, 1 positive, plus 2 hydrogen ions, H1 positive, plus an electron, reacting to form VO, 2 positive, plus water, H2O. And this is listed on my table with a standard reduction potential of 1.00 volts. All right, so we've located now the reactions which are involved in this process, but remember, these are both reduction potentials, and as such, I'm going to need to figure out which of these reactions needs to be flipped and run as an oxidation to yield a galvanic cell that is a spontaneous forward process. And a quick examination of my 2 half reactions here shows me that the standard reduction potential labeled for my zinc half reaction being negative needs to be flipped such that I can yield a positive overall cell potential when I add the 2 half reactions together. So I'm going to go ahead and flip now, leading to now an oxidation reaction described as elemental zinc reacts to form a zinc 2 ion in solution by releasing 2 electrons. And as I've now reversed that reaction, making it into an oxidation, I also need to change the sign on the half cell potential, meaning this is now a standard cell potential for this half reaction of positive 0.76 volts. All right, so we've now taken care of the oxidation step. Let's now take a look at the reduction step for our vanadium half reaction. Looking at this here, it seems to me that we need to balance our electrons to make sure that we are showing conservation of those electrons throughout the course of this redox reaction. I'm going to go ahead and multiply the entire reduction step here by a common factor of 2. And as I do so, that now yields a reduction reaction of 2 VO2, 1 positive, plus 4 H positive, plus 2 electrons, reacting to form on the product side now, 2 VO, 2 positive, plus 2 H2O. And now that I've got my electrons balanced, I can go ahead and combine together my half reactions to get the overall redox reaction that is occurring within this electrochemical cell. I'm going to notice here that the electrons will cancel out on both sides, and adding together yields here now the overall reaction of zinc elemental plus 2 VO2, 1 positive, plus 4 H positive, reacts to form on the product side, Zn2 positive, plus 2 VO2 positive, plus 2 H2O. And again, I'm now going to sum together the cell potentials of my oxidation half reaction and my reduction half reaction, yielding a cell potential of this cell under standard conditions of 1.76 volts. Now, I've got a standard cell potential, but this cell is not operating under standard conditions. We have a variety of different concentrations of the aqueous species present here, which implies now it's time to apply the Nernst equation to calculate the cell potential of this cell as it operates under these non-standard conditions. From our previous slide, recall that the operating cell potential, E cell, is equal to the standard cell potential minus the factor RT over NF times the natural log of Q. Now, before we move forward to do the actual calculation, let's first calculate a value of the reaction quotient Q for our system under its current conditions. As always, Q is given as the ratio of the concentration of the products over the reactants raised to the respective exponent powers of the coefficients from the balanced chemical equation. So I'll go ahead and write out the value of Q here for our operating system would be the concentration of my product, Zn2 positive, times the concentration of VO2 positive, which is going to get squared from its balanced equation coefficient, all divided by, now on my reactant side, the species, we've got VO2, 1 positive, that's also going to get squared. And they're going to multiply that by the concentration of hydrogen ions to the 4th power. And recognize here, folks, that I have left out of my system here both the presence of the elemental zinc metal as a solid phase species does not get included within a K expression or a Q expression. And also the liquid phase water will also not be included within that Q expression as well. So I've got a defined ratio for Q. Let's now go ahead and plug in the given concentrations from our described cell. Zinc's concentration was given as standard concentration of 1.0 molar in my numerator. The species VO2 positive was given to me as a concentration of 0.010 molar, and again, that value is getting squared. And then in my denominator, the species VO2, 1 positive, that was given to me as a concentration of 2.0 molar, which again, I'm going to square. And we're going to multiply that by the hydrogen ion concentration, which was given as 0.50 molar, which is going to get raised to the 4th power. And plugging in those values into my calculator, I get here a calculated value of the reaction quotient Q of 4.0 times 10 to the negative 4th. All right, so I've got a value of Q. Let's now return back again to our Nernst equation. Looking at the Nernst equation, the standard operating cell potential, which we had calculated above, was 1.76 volts. I'm going to subtract from that the factor RT over NF times the natural log of Q. That R value, again, is 8.3145 joules per mole Kelvin, times a operating temperature, assuming standard conditions, of 298.15 Kelvin. We're going to divide that now by the 2 for the number of moles of electrons which were present in our system, and also in our denominator here the value of Faraday's constant, that is 96,495 coulombs per mole of electrons. And that entire ratio is going to be multiplied by the natural log of our reaction quotient Q, which in this case is the natural log of 4.0 times 10 to the negative 4th. And I'm going to go ahead and plug all that into my calculator. And notice here that the Kelvin and Kelvin are going to cancel. And I end up here also canceling out moles of electrons there, leaving me here with units of joules per coulomb, which again sounds a whole lot like a volt. And as such, I find an operating cell potential of this particular cell under these conditions of 1.86 volts. And take a brief moment here to think about why that makes logical sense. The Q value, as described by the current concentrations of our reactants and products within this system, is a very, very small value of Q, implying, therefore, currently this system has a relatively higher concentration of reactants than products, which should, therefore, drive this reaction in the forward direction. And as there's a larger driving force in the forward direction, I would expect that electromotive force, that cell potential here, to be larger than it would be under our standard conditions. And as such, we see it operating now at that cell potential of 1.86 volts, greater than the standard operating cell potential of 1.76 volts. So all that seems to check out. And last but not least is a little bit of cleanup here. I'm going to go ahead and finish up labeling our diagram. We've got here the cathode, again, the place where the reduction occurs. That's got to be our vanadium half cell there. That platinum cathode is labeled now on the left side of our diagram. And then we also have on the right side of our diagram the anode, again, the place where our oxidation occurs. That oxidation was the oxidation of our elemental zinc. So that anode is composed of the zinc metal. And I've also labeled for you here on this the direction of electron flow. Recall, oxidation occurs at the anode. As such, those electrons are released from our anode and will travel, therefore, from right to left across our wire in that diagram from the anode towards the cathode. And a tiny bit of finishing cleanup there, I can just go ahead and label the identities of the species present in both the cathode and the anode. On the cathode side, again, we have the place, again, where our reduction occurs. Those species are the VO2 1 positive ion at 2.0 molar, the hydrogen ion at 0.50 molar, and the VO2 positive ion at a concentration of 0.10 molar. And then present again in the anode beaker there is the zinc ion solution at a concentration of 1.0 molar. All right, so we've now completed thoroughly a large problem here relating to electrochemistry. Let's move on to our final two slides. All right, on our last two slides here, we're going to do one more little bit of equation rearranging magic here, this time in an attempt to relate the equilibrium constant, Kc, to the operating cell potential of an electrochemical cell. Now, as a starting point here, note that for a system which is in equilibrium, the favorability of the forward process is exactly balanced by the favorability of the reverse process. That is to say, there is no net driving force pushing electrons from one location to another within the system. Implying, therefore, an electrochemical cell at equilibrium would have an operating cell potential of 0. And also recall from our conversations around equilibrium chemistry that at equilibrium, the value of the reaction quotient Q is equivalent to the value of the equilibrium constant, KEQ. With these two ideas in mind here, let's now go back and revisit our Nernst equation. Recall the Nernst equation was given as the operating cell potential is equal to the standard cell potential, that is E naught, minus 0.0591 over n times the log of Q. And again, if I recognize that if I have a system which is in equilibrium, the operating cell potential would be equal to 0, and the value of Q is equal to the value of KEQ at equilibrium, I could then state that the operating cell potential of 0 would be equal to the standard cell potential minus 0.0591 over n times the log of KEQ. And just a couple of quick bits of equation rearrangement here to solve here. I'm going to go ahead and add that factor of 0.0591 over n times the log of k to both sides, and that gives me the expression the standard operating cell potential E naught cell is equal to 0.0591 over n times the log of k. And then I can then simply multiply both sides of the equation by n and divide by that factor 0.0591, which yields an expression now here that the log of the equilibrium constant, KEQ, is equal to n times the standard operating cell potential divided by 0.0591. And think for a moment here, folks, about what a powerful equation this actually is. Because this equation will then, therefore, allow me to calculate values of the equilibrium constant, KEQ, by measuring simply the operating standard cell potential of a particular electrochemical cell. And this is a big deal. This is another one of those linking concepts that will link together two big areas of chemistry. I now have a tool that links directly together equilibrium constants with cell potentials. So this powerful equation here can be used to good effect, and we'll see that on our next example problem. Let's have a look at our last slide. All right, for our last slide here, let's go ahead and apply the equation we just derived on our previous page, in which we're going to calculate here a value of the equilibrium constant, Kc, for a redox reaction. We're going to provide you information here that we've got a galvanic cell constructed using the half reactions which are described on our page here. Those half reactions are: number one, we're going to be taking the ion S4O6 to negative and add 2 electrons to that in a reduction in order to form 2 S2O3, that is thiosulfate ions with a -2 charge. The operating cell potential for this half cell is 0.17 volts under standard conditions. And then for our second half reaction here, we're going to give you here a reduction reaction, which is the chromium 3 ion, Cr3 positive, picking up an electron to form a chromium 2 ion, Cr2 positive. And the given reduction potential for this half reaction is negative 0.50 volts. So let's go ahead first of all and recognize that yet again we need to have a operating galvanic cell here, which must by definition have a positive voltage, and so I need to flip one of these half reactions to turn it into an oxidation half step. And looking here, it makes more logical sense for me to flip the second given reaction, that is one involving our chromium ions, turning this now into an oxidation half reaction in which the chromium 2 ion, Cr2 positive, is giving up an electron to form a chromium 3 ion, Cr3 positive. And as I'm currently again flipping that half reaction, I'm going to also need to change the sign on the operating cell potential here to a potential of positive 0.50 volts. All right, so now I've got identified my reduction half reaction and my oxidation half reaction. A real quick cleanup here, I'm going to need to recognize that to balance electrons, I'm going to have to multiply that entire chromium reaction by a common factor of 2 to conserve electrons within this redox process, yielding now 2 Cr2 positive reacting to form 2 Cr3 positive plus 2 electrons. And I can now go ahead and combine together those half reactions to get the overall redox process occurring. This gives me here the ion S4O6 2 negative plus 2 Cr2 positive ions on my reactant side, reacting to form my products here, which is 2 S2O3 2 negative plus 2 Cr3 positive. And again, adding together the reduction potential of the reduction half reaction with the oxidation potential of that oxidation half reaction yields for me here a overall operating cell potential of 0.67 volts under our standard conditions. So we've got E naught. Let's now go ahead and use that equation which we had derived on our previous slide here, which relates the equilibrium constant Kc to that operating cell potential E naught. From the previous slide, we derived the equation: the log of the equilibrium constant K is equal to the number of moles of electrons transferred N times the standard operating cell potential E naught divided by the factor 0.0591. And I'm going to go ahead now and plug in the values that relate to this particular system. The number of electrons being transferred within this redox reaction is 2. I've got an operating cell potential of 0.67, and I'm going to divide that by the factor of 0.0591. Just going to go ahead and ignore units for the time being, recognizing that again I'm solving for an equilibrium constant, which itself is a unitless value. And as I plug in those values here, 2 times 0.67 divided by 0.0591 gives me here a value equivalent to 22.673 off of my calculator. And again, that value is equal to the log of K. And all that I need to do now to solve for K is to recognize that the inverse of a log operation is in fact an exponent. So I'm going to go ahead, therefore, and say 10 to the 22.673 power would be therefore equivalent to our value of the equilibrium constant Kc. And that gives me a value, as I plug into my calculator, of approximately 4.7 times 10 to the 22nd. So we've got a calculated value of the equilibrium constant Kc. Let's think for a quick moment about what that means. This is a very, very large value of K, which should imply, therefore, this system heavily favors the formation of products at equilibrium. But that should make logical sense again, because for this redox reaction here, we see we have a positive operating cell potential, which again should tell me here that the forward process is a favored process for this galvanic cell. So it's not uncommon to have very, very large values of the equilibrium constant Kc for these redox reactions that we deal with. All right, so we see some major links between the ideas proposed in Equilibrium and our current topics of conversation around cell potentials here. Another tool that we can see used on the AP Chemistry test to kind of link together the big units of study that often get linked in free response questions. All right, thank you so much for listening, and we'll see you in our next lecture.